So, let us come to lecture 14, where we will be summarizing the performance results. So, what we have seen till now is that using real programs for benchmarking. So, it is very much essential that the benchmark should consist of set of programs, and those programs should be very much relevant. Now, how to consolidate all the runtimes and come up with a single metric that can be used for comparison. So, we have seen that millions instruction per second is something we are calculating. We are calculating the total execution time. So, we have so many metrics now. Now let us say I have these metrics, and I can say that a machine A is performing some set of tasks which is taking so and so time. A machine B is also executing the same program and it is taking so and so time. Another set of program is also being executed by both the processors and they are giving some time. Now, it may happen that A is giving better result compared to B for program 1 and B is giving better result for program 2 as compared to program 1. Now, how can you tell that which processor will be better? So, we shall be discussing several measures that are used for this consolidation basically. Coming to what is reproducibility. By the term reproducibility, we mean that can we reproduce the same thing? Can we have the same result? Now, imagine when can we have the same result? Let us say I have done a program for certain job and I am getting a result. Now, I should also say that it is not only that same program will get executed in other machine and we will check the result. I have to also give some more details. What are those some more details? Like, what is the execution environment that I am using? How much is the disk utilization? What kind of cache memory I am using? What are the other features along with that program when you are executing? So, you have to give all those parameters or all those things that is there along with that program. Not only this program I have made it this way, along with that what are the other things that are going on at that particular time, the swap space, how much swap space is possible and so on and so forth. So, actual runtime of a program on a machine depends on so many factors. One is the degree of multiprogramming, like whether you are using multiprogramming or not, disk usage, how much disk usage is being done, compiler optimization. So, reducibility of experiments is very important. That means, anyone should be able to run the experiment and get the same result. This can only happen again if you actually do the same thing that other computer was doing for executing that program. So, benchmark must therefore specify the execution environment very clearly. For example, the spec benchmarks mention details such as extensive description of the computer and the compiler flags. So, spec benchmarks is not only giving you a program, along with that program it is giving you some more details such that you will be able to reproduce the same thing if you execute that particular program. Hardware, software and baseline tuning parameters like the swap space, you can say, like the cache memory, how much cache memory you are using and so on and so forth. So, how to summarize performance results? The choice of a good benchmark suit that relates to real applications is essential to measuring performances. So, the meaning is the choice of a good benchmark suit is really very important. For a single program, it is very easy to say that which computer runs faster, but will it be equally easy when you have number of programs running on different machine and you are getting different results? how can then you say that this computer performs better than the other? Let us see this example where program 1, this is CPU A, CPU B and CPU B, 3 different processor. In seconds, program 1 is taking 1, this is taking 20 and this is taking 25 and these are taking this. So, total time taken is this, total time taken is this and total time taken is this. Now, let us see, we can make the following statements which may depict a confusing picture when considering together. So, if you consider it separately, okay. So, program 1 A is the fastest, it takes 1 second, and program 2 B is the C is the fastest, we can say. Now, let us say this with respect to A. A is 10 times faster than B. Very true. A takes 1 second, B takes 10 seconds. Similarly, B is 2 times faster than A for program P2. This is for program P1. Okay. Now, B, which is taking 250 seconds, and program P2 for processor A, it is taking 500. So, this is taking twice this time, this is taking twice this time. So, we can say B is 2 times faster than A for program P2. Again, A is 25 times faster than C for program P2 and C is 50 times faster than A for program P2, because P2 this takes 500, this is taking only 10. Similarly, you can find out B is 2.5 times faster than C for program P1, C is 25 times faster than B for program P1. Now, how can I say which processor is the best? It is more confusing rather than getting some inference, right? So, how to summarize this performance result? Let us see how we can do this. The choice of a good benchmark suit that relates to real applications is essential to measuring performance. So, for a single program it is very easy to say, but however, when there are multiple programs the comparison may not be so straightforward. So, we need to come up with some solution. So, let us see the total execution time first. What is the total execution time? For CPU A, the total execution time is 501, CPU B, the total execution time is 260 and CPU C, it is 35. Based on this measure, what we can see or what we can comment is B is 1.93 faster than A for 2 programs. Now, we are not taking into consideration individual programs. Now, we are saying something in terms of both the programs. C is 14.31 times faster than A for 2 programs and C is 7.43 times faster than B for 2 programs. If the actual workload consists of running P1 and P2 unequal number of times, again this is something else. First we have given 2 programs and we are saying this is the execution time, and now we are saying that these programs how many times it will be running. So, the frequency of running those programs is now coming into picture. So, if the actual workload consists of running P1 and P2 unequal number of time, this measure will not give the correct result either. So, now let us come up with something called arithmetic mean. So, this is defined as the average execution time for all the programs in the benchmark suit. So, this is the average execution time. So, by average execution time, what we mean is that we are averaging the execution time summation of all divided by n. This is your arithmetic mean, where xt denotes the execution time of ith program and there are n programs. Similarly, what is weighted execution time? If the program constituting the workload do not run equally, as I said, program A can run more time than program B. for some processor program B can run more times. So, based on this, that means frequency of that program executing. So, based on this, how you can calculate. So, for this, if 40% of the task in workload is program P1 and 60% is program P2, we can define some weights associated with these programs. So, program P1 is having 0.4 weight, W1 is 0.4 and W2 is 0.6, because P1 it is 40% of the task of the workload in program and 60% for P2. Now, we will see two alternative methods. One is weighted arithmetic mean, another is normalized execution time. Now, arithmetic mean we have already seen. Let us see what is weighted arithmetic mean, WAM. It is computed as the sum of products of weighting factors and the execution time. So, we are not only considering only the execution time, we are taking into consideration the execution time and the weights associated with that particular execution time, where Wi denotes the weighting factor of program I and can be written as, this is the weighted arithmetic mean, where I multiply Wi into execution time of I and we get the sum. Now, let us see these two programs again, CPU 1, 2 and 3. So, weight for first one is 0.50 and weight is 0.50. So, we get weighted arithmetic mean of A as 250.5. How we are getting that? Let us see this. So, here you can see that 0.50 is multiplied by 1 for program P1 for CPU A. So, this is CPU weighted arithmetic mean for A. We are multiplying this weight multiplied with the time, that is 1, and similarly we are multiplying 0.50 into 500, which is for program P2. This is for P2, this is for P1, and we are getting weighted arithmetic mean as 250.5. So, here we have calculated that for all. So, weighted arithmetic mean for A is 250.5, weighted arithmetic mean for B is this and C is this, depending on these values we have calculated and depending on these weights. Similarly, if you change the weight of these, now the weighted arithmetic mean is different. Again, if you change, the weighted arithmetic mean is different. So, we here also we show you that how we can calculate the weighted arithmetic mean for several CPUs given the program and given the execution time for some programs. Now, coming to normalized execution time. So, as an alternative, we can normalize all execution time to a reference machine and then take the average of the normalized execution time. So, now we are saying that there will be a reference machine and with respect to that reference machine we will be calculating this. So, we are normalizing it with respect to a reference machine, followed in spec benchmarks where a Spark station is taken as a reference machine. So, what will be the average normalized execution time? So, this can be expressed as execution time. What is XTR? Execution time with the reference Ri, XTR I, and summation of all of this with that reference we are doing it, with that reference machine. So, one machine can be taken as a reference and rest can be calculated based on that. We will be seeing that next. That is called normalized arithmetic mean, which is execution time of the with respect to reference machine, summation of that by n. So, here XTRI denotes the execution time for ith program normalized to the reference machine. So, this is for the ith program normalized with respect to some reference machine. This is normalized geometric mean. Earlier it was normalized arithmetic mean. Now, we are going to normalized geometric mean. Now, let us see how do we compute this. So, program 1 is the same parameters that we were using. Now, see what we are doing. These values we are calculating by with respect to normalized to A. That means, when we are saying normalized to A, we are making 1 here. These two will become 1, and with reference to that, what is these values? So, now see, this is 1, 10 divided by 1, 25 divided by 1. Similarly, this one is, how do you get 1 here? You will get 1 here by dividing by 500. So, this has become 1. You divide by 500, it will become 0.5, and you divide by 500, it will become 0.02. So, all these values are normalized with respect to A. Let us see how do we normalize with respect to B. Similarly, when we say we normalize with respect to B, then we have to make all these as 1, 1, 1. Initially it was 10, this was 250, and this was 250. This is 10 and this is 250. So, what we are doing? We are making others reference normalized to B with reference to B as a reference one. So, what we are doing? This is 1 divided by 10, and this will become 25 divided by 10, and here it was 250. So, you have to divide it by 250. So, we are dividing 500 divided by 250, 1 to make it 1 we divide by 250. So, we will get here 1 and 10 divided by 250. So, just see this, what we are getting. We are normalized this with respect to 1, we are making this as 1, and now these are the two values which we are getting. And similarly, we have normalized this to C, where these two have become 1, and we are getting this value and this value with respect to C as the reference machine. Now, once we are done with this, we calculate the arithmetic mean. We calculate the arithmetic mean, we calculate the geometric mean. Now, see, arithmetic mean, still we cannot say which one is better. So, in this case this is 1, in this case this is 1, and in this case this is 1. Okay. So, it is very difficult to come up with a conclusion based on this, but you see the geometric mean. Geometric mean seems to be consistent. C is taking, C is the least, C is the least here also, C is the least here also. So, the geometric mean is considered as one of the metric that can be used for evaluation, although arithmetic mean cannot be used properly. So, in summary, what we can say that in contrast to arithmetic mean or geometric mean, normalized to the execution time are consistent no matter which machine is the reference one. So, what we have seen? We have made A as a reference machine, then also C performs the best. We have made B as the reference machine, in that case also C is giving better, and when you are making C as the reference machine, then also it is giving better. So, the result seems to be consistent even if different programs are executed different times. Hence, arithmetic mean should not be used to average normalized execution times. But there is one drawback of geometric mean, that they do not predict the execution time. You cannot give a prediction of the execution time, but it is consistent because it is giving that value where C seems to be better, And it also encourages hardware and software designers to focus their attention to those benchmarks where performance is easiest to improve rather than the ones that are slowest. So, we generally improve where the requirement is high. That means, certain instructions are executed more, we try to improve that part more. Certain instructions are executed less, but that does not mean we will leave that part also. That part also we should take into consideration, but it generally encourages the hardware and software designer to focus attention at those benchmarks where performance is easiest to improve. That is the thing. So, we came to the end of this lecture. So, in the last 3 lectures, what we have tried to show is what is performance, what performance metrics can be used, and how we can actually finally say that, okay, if you use certain metric, then this you can finally conclude that which one is the best, which one is the worst. Thank you.